Hi, I'm Zor. Welcome to Unizor Education. Today we will talk about Lagrangian in generalized coordinates. This lecture is part of the course called Physics Plus, and in particular the whole chapter is about Lagrangians, and we have already covered certain information about certain topics about Lagrangian, and I do presume that you know everything we were talking before about this, and that includes, for example, variations. So we have to understand what is the variation of functional. In this particular case we will use it definitely, and also the previous lecture about Lagrangian mass is also very important because it introduces uniform Cartesian coordinates and transformation of coordinates. Now, today we'll talk about Lagrangian in generalized coordinates. Generalized means basically any kind of coordinates, which definitely can be very smoothly related to Cartesian coordinates. It's transformation. For example, on the plane we have Cartesian coordinates with two perpendicular axes, and we have, let's say, polar coordinates. In space we have cylindrical coordinates, spherical coordinates, and Cartesian. So these coordinate systems are basically equivalent in some way because they uniquely identify a point in space with certain number of real numbers. In case of a plane it's two numbers, in case of a three-dimensional space it's three numbers, and in case of n-dimensional it's n numbers. So we're talking about systems with n degrees of freedom, so that's where n numbers actually come from. So now this lecture is about applicability of using Lagrangian and Euler-Lagrange equation, which you already are familiar with from the Cartesian system, applicability to generalized coordinates. So the point which I would like to actually make is that the same approach, which is Euler-Lagrange equation and solving this equation with certain initial conditions, is applicable in any system of coordinates, versus, let's say, Newtonian second law, which is only applicable to Cartesian coordinates, because there are forces involved, accelerations. What's acceleration? Acceleration basically is a vector. It has three components along each axis, x, y, and z. So that's exactly the most important part which I would like to convey today, that while Newtonian approach is great for Cartesian system, in some cases when we would like to use some other non-Cartesian system, Euler-Lagrange is applicable as well. Newtonian not as much. Let's put it much more difficult. So the beauty of the Euler-Lagrange equation is that this is exactly the same equation. I'll write it down. It's dl by d, let's say si, equals d by dt, dl by dsi, time derivative, where L is Lagrangian, L is kinetic minus potential energy. Obviously S is coordinate, a generalized coordinate. It can be anything. For example, if you have a, let's say, the pendulum, you probably have an angle as one of the parameters, right? Coordinates, so to speak, instead of Cartesian. Angle is much more convenient in this particular case. So in this case, S would be an angle. But the form of this equation is the same. Obviously, K, kinetic energy, it depends on velocity and sometimes on position. U is potential energy, which depends only on position. We are talking only about conservative systems right now, when there is a potential energy of the system, and again we already learned that partial derivative of potential energy by each coordinate is actually a force in Cartesian coordinates. So for any conservative system with any system of coordinates, generalized coordinates, this equation is exactly the same. Versus Newtonian second law, which definitely changes the form. F is equal to m times a is only for Cartesian system. For, let's say, polar system, it's already completely different. Okay, so that's the beauty. I would like to prove that this is exactly the case, that we can use exactly the same equation for any system of coordinate. And that's a very big advantage over Newtonian approach with second law, F is equal to m times a, which changes basically the format of the equation in any other non-Cartesian system. Okay, now you basically know everything to just come logically without any kind of conclusions related to calculations, etc., etc., to come up with the validity of my statement that this equation is good for any generalized coordinate system. And what I'm going to do in this lecture is I will talk about logical foundation of this particular statement, why it's really the case. And I will leave details, and there are some details actually, to written notes for this lecture, which are presented exactly where the lecture is, which is unizor.com. You go to Physics Plus course, you take the Lagrangian chapter of this course, and the lecture is called Lagrangian and Generalized Coordinates. So there are much more details in that particular text, and I was actually working quite a long time on it to make it, well, perfect to my personal liking. So I will just give you the logic of this without small details, and then I definitely encourage you to read the notes. So what is the logic? And again, as I said, you know everything about this particular thing. It's just a matter of putting whatever you know in the proper sequence, so you will come up with the result of universality of Euler-Lagrange equation. Okay, let me start from the beginning. In the beginning, we were talking about Newton's second law in Cartesian coordinates. Okay, so Newton, Cartesian. Now, the Newton's second law in Cartesian coordinates, which we have basically used to use from school, we take it as axiom. So there is no proof. This is axiom. It's based obviously on experiments, etc., etc., and it was confirmed many times. So whatever it is, we take this as given. So Newtonian second law is applicable to systems. In this case, we're talking only about conservative systems, but it's applicable in more universal way. But in this case, only about conservative systems. So this is the law. This is an axiom. We take it without any kind of logical base or whatever. We take it as is. All right. What we did next, and again, we already have done it, in one of the previous lectures about Lagrangian in n-dimensional space, we have proven that this Newtonian second law in Cartesian coordinates is equivalent to Euler-Lagrange equation, again in Cartesian coordinates. So that's also done. And that was proven. And the proof actually is very simple, because you start from F is equal to m times a. Now F is basically a partial derivative. Every component of F is a three-dimensional vector, right? So every component of F is partial derivative of potential energy by corresponding coordinates. And acceleration looks exactly like this. Acceleration is first derivative of the velocity, and velocity again was very easily derived from k. K is equal to 1/2 mv squared. So if you will take first derivative, you will have basically mv, which is the velocity. Again, we're talking about vectors, so it's very easy to do, and we have done it. So this is the first step which we have proven. Newton's Cartesian in Cartesian system is axial, and we have we have proved that Euler-Lagrange is completely equivalent to this for conservative system in Cartesian coordinates. Okay, so Euler-Lagrange is done, but only in Cartesian coordinate system. We want to prove it for generalized, but again, how do we do it? Next thing, let's just think the following. Any trajectory, well, the purpose of physical law is to derive analytically the trajectory of the system from, let's say, point A to point B. Now, trajectory is a physical reality. I mean, it doesn't really matter what kind of coordinate system we introduced in our three-dimensional world. Trajectory from a point to a point, how the system actually is progressing, is not dependent on this coordinate system. What is dependent is our mathematical model of this trajectory as a set of functions of time, coordinate functions of time. So if we have coordinates which is a function of time, and that may be multiple, obviously, for multiple dimensions, S1, S2, S3, etc. All of them are multiple, are functions of time. So if we have these coordinates, then this is just a description of physical reality in our system of coordinates, where we have introduced all these coordinates S. So this is a very important to understand, that there is a physical reality which is independent of observer from our introducing coordinate system, and our mathematical model which describes the physical reality in the terms of functions of time. Now, let's assume what we do further about this. Now, from this, we are completely going to another topic. In the topic which was called variations, we have found a very interesting thing, that integral of L of t bt from t1 to t2, where L is Lagrangian, this is called action, has extremum which satisfies this equation. So forget about coordinates. This is function of one argument, time. Let's call it time. And you have basically this integral. Actually, what exactly is L doesn't really matter. I mean, I'm saying right now it's a function of time, any function of time, basically, relatively smooth. And what I'm saying is that if this function is actually a function of time which is function of coordinates, so it is function of time, but not explicitly. So explicitly it's a function of coordinates, but since every coordinate is function of time, this makes it a function of time. Now, if I would like to have an extremum of this action integral, I have to actually solve this equation. This is part of the variations lecture which we have already covered. So what's interesting is that on one hand, Euler-Lagrange equation is supposed to be equivalent to Newton in Cartesian system to deliver trajectory. On another hand, if we will take this integral along this trajectory, because this is integral by time actually, we are integrating, which means we are making, starting from t1, we make an infinitesimal increment of the time, and we are multiplying the value of function, whatever these coordinates are determining a point on the trajectory. And then we are multiplying by this infinitesimal time, and then do again increment again, and basically add them up together. This is a physical reality. That's what I want to say. Regardless of the fact that this is coordinates, we are moving along a physical trajectory. So we are incrementing the time on a physical trajectory. Let's just forget about coordinates. So what do? We increment the time. Now this points to a point on the trajectory. We calculate the function, which is basically a difference between energies, which are physical realities, not related to coordinates. So no matter how we calculate coordinates, this function actually is a function of a point on the trajectory, which means it's a real function independent of coordinates. If instead of s1, s2, sn, I will take, let's say, q1, q2, qn, completely different coordinates, which is transformable, obviously, into Cartesian, it doesn't really matter. The result will be the same. Point s1, s2, sn, at the same moment of time t, is exactly the same on the trajectory as point q1, q2, etc., qn, if it's the same moment of time. So no matter which coordinate system we use, this is a point on a physical point on the physical trajectory, and in that point we are calculating the difference between kinetic and potential energy, which is also a reality, independent of our coordinate system. So that's why what I'm saying is that this integral is physical reality regardless of the system of coordinates. No matter what the system of coordinates, the point will be the same at the same moment of time t. If I will take other coordinates, q1, q2, etc., the function L is a function of a point on the trajectory, which is energy related, which is a scalar, again not related to any kind of coordinate system, and integral by time. So it's not related to coordinate system. So this is functional, not related to coordinate system, related only on the trajectory. Now, if this integral of this functional is related basically only on reality, so among all the different trajectories between 2 points, this real trajectory along which the system is moving is the one which is a solution to this equation. And this is the theory of variation, again, not related to our today's physics, whatever. So what's interesting is that on one hand, Euler-Lagrange gives you a real trajectory because it's equivalent to Newtonian system in Cartesian system of coordinates. On another hand, the same equation gives you trajectory as a extremum of this functional, and this functional is again depends only on physical trajectory. So it looks like we can find the trajectory using, well, 3 different approaches. Well, in Cartesian system, only one approach, which is Newton-Cartesian. Another approach in Cartesian system is Euler-Lagrange equation, which was basically analytically derived from Newtonian. But on the other hand, in any system of coordinates, this trajectory is the one which extremizes the value of this functional. And how to find this trajectory in any system of coordinates? Just solving this particular equation. But trajectory must be one and the same, which we are finding, no matter what way. We are finding it using Cartesian coordinates, or with Euler-Lagrange equation, or we are using Euler-Lagrange equation to solve this, to minimize or extremize the value of this functional. So that's what's very important. It's exactly the same trajectory, which means that the result of this Euler-Lagrange equation in Cartesian coordinates should give exactly the same trajectory as Euler-Lagrange equation that extremizes this functional, no matter which system of coordinates we are using. And that's what's the most important part of it. That's why we can use Euler-Lagrange equation in any system. So again, in Cartesian it gives the real trajectory because it's analytically derived from Newton. But in any system of coordinates, it gives the minimum of this functional, or extremum of this functional. And that's the logic behind ability to use Euler-Lagrange equation in any system of coordinates. Because extremizing this functional is independent on system of coordinates, because this point is exactly the same no matter which system of coordinates you're using. Therefore, the value of the function L is independent. So L, one way is, let's say, in system of coordinates S, Lagrangian looks like this. But in some other system, let's say in coordinates Q, kinetic and potential energy formula looks differently. That's why I put an index LS and LQ. Formulas are different. So in this case is this one. But for any particular moment in time t, this gives real coordinate, this real point on a trajectory, which is exactly the same point as this one. And since Lagrangian is the difference between potential, kinetic and potential energy, they must be equal. So consider it as a function of t, because ultimately these are functions of t. These two functions of t are identical. This looks differently, but if you will forget that how it looks using coordinates, and you will just have a value of time t, and then you calculate this, and you will have exactly the same result if for the same time t you will get the same point in different coordinates and different formula, but exactly the same result. And by the way, in notes for this lecture, which I was mentioning before, and I'm encouraging you to read it, I do have an example actually in Cartesian and in polar coordinates on a plane. I calculate I think I calculate the square of velocity, which is square of magnitude of velocity. And yes, it's proven analytically that they are the same. And since square of velocity is the same, obviously kinetic energy is the same, and potential will be the same, because potential energy depends only on the point, and points are the same, physical point in space. So basically this is a logical explanation of why Euler-Lagrange equation can be used in any coordinate system. And again, here is the very, very briefly the logic, steps of logic. From Cartesian Newton, which is axiom, we derive analytically that Euler-Lagrange equation in Cartesian coordinates gives you the trajectory. On the other hand, if you will consider this functional, which is basically independent of system of coordinates, extremizing this functional is also the same equation. So we can get equation of the trajectory, we can get a trajectory in Cartesian system coordinates, either this, solving Euler-Lagrange equation in Cartesian coordinates, or extremizing this functional. Forget about how. But now the functional is independent of system of coordinates, and trajectory is independent. So whatever we find in one system of coordinates must be exactly the same as we find in another. Minimum of this particular functional is independent, as the functional itself is independent of coordinates. It depends only on which trajectory we choose. And that's why, since we can do this particular minimization or extremization of this functional independently of system of coordinates by solving this equation in whatever coordinate system we have chosen, that means that we will always have exactly the same result, the same trajectory. Okay, that's basically all I wanted to talk about. And what's exactly very, very, very important is for you to read the notes for this lecture, where I'm basically explaining the same thing, maybe better, because I was kind of thinking about each statement which I was making in writing. And there are some more details. For example, details about how one coordinate system is transformed into another. It should be a smooth transformation both ways. And then there is an example of deriving some particular value which depends only on trajectory, like for example square of magnitude of velocity in each point. It depends only on the movement, how you move, not which coordinate system you introduce. The same way if, for instance, you take the length of this curve. The length of this curve doesn't really depend on which coordinate system you use, how you define this particular curve. So no matter what it is, you still have some physical reality as a result, which is independent on coordinate. And an energy in every point on the trajectory is independent of us who are establishing certain system of coordinates, describing the trajectory as a function or a set of functions, and then we calculate the energy. Energy is energy. It's a physical reality. And so is action integral. So the action is basically a physical reality, and extremization of this action among different trajectories is also physical reality. If it's the same value regardless of the coordinate system on this particular trajectory, it's the same on that particular trajectory regardless of the system. So which trajectory delivers the extremum of this function, or it's a minimum or maximum or whatever, is again physical reality, independent of the system of coordinates. And that's why we can use the Euler-Lagrange equation in any system of coordinates, because it actually defines the trajectory which extremizes the value of the action function. Okay. I prefer to repeat the same thing more than once in this particular case. Again, read the notes, and it's very important. Other than that, that's it for today. Thank you very much, and good luck.